right, so we're looking at this one impulse on a baseball, and parts considering the situation. All right, assume that the force is constant. What is the magnitude of J, the impulse on the ball? Okay. So for that first part, what I would have in my Y is really showing my understanding of that. I understand what impulse is. That impulse is created when a force acts for a time on a body. So, and they want the impulse. So I'm gonna switch to my how real quick and grab my equation for impulse. And I really only need the first half of this. And let's see what information they give me. They tell me that better so he gets a good solid hit. He applies the force of 1,200 newtons to the ball for 0.7 times 10 to the minus 3 seconds. Okay. So back here, that means my force is 12,000 or 1,200? 12,000 newtons. My delta time for me was 0.07 times 10 to the minus third. Yep. Times 10 to the minus third seconds. And that equals J. And so I would do my math. You guys need me to do the math on that, or are you good on that, you think? Yeah. Okay, so you're good on the math there? Think so? All right, good. Can I do that? Sure.
Does it matter if you put it with the like calculator figure?
Yes. Yep. So yeah, you need scientific notation tells you in a way how big the number is. So you can't 0.7 and 0.7 times 10 to the minus 3 are vastly different numbers.
Oh, I meant if you did like 0.000.
Oh, if you put it into non-scientific notation, that's fine. That's fine. Yeah. Okay, so to do this math, I type in the numbers into my calculator, separate by multiplication, and I hit enter, and I get my answer of 8.4. And since I multiplied newtons by seconds, that's Newton seconds. Yep. All right. Stop me if you have questions. Otherwise, I'll assume you're good. So, the magnitude of net force versus time graph has a rectangular shape. It does. Often in physics, geometric problems have physical meaning. On this graph, the length of the rectangle corresponds to the impulse. So let's see, what did we just do to find the impulse mathematically? Let me remind you, what did we just do back here to find the impulse? Anybody tell me what I did here? What mathematical operation? Multiplication. And what did I multiply together? Newtons and seconds. And what does the newtons represent? And what does the seconds represent? Time. All right. So back here, if I take, and which axis represents force? The vertical or the horizontal? Come on, it's gotta be one of them. Vertical and time. So looking at that geometric shape, multiply its height by its width. What do I get? Area, and the area is the impulse. Area. Hey, and I got it correct. And then they have figure 2 here. As a more realistic example. If both the graph represents the constant net force, the graph representing the variable net force represents the same impulse acting on the baseball. Which geometric property must the two graphs have in common? Nobody? Okay, moving on. Area, right. Because that's the impulse. So if they share area, that's that. Yeah? So, assume that a pitcher sends the baseball to the travel in a straight line parallel to the ground. Batting the ball so it goes directly back to the pitcher along the same straight line. Define the direction the pitcher originally throws is positive. The impulse on the ball caused by bat would be in the, let's see. Its momentum, we got to draw a little picture now. Over here. Momentum of the ball was this direction, which we're calling positive. And then the batter hits it, and it's going that direction. What would that direction be? Negative. So, if we use the equation that they gave us here, right? Where is it? This one here, we'll use that just. And we go, okay, well, I'm going to show the J. So, as the math, I'm going to have a negative V minus a positive V. If I have a negative minus a negative, that's going to give me a positive or a negative answer. A negative answer. So no matter what those values are, I'm going to have, like in this case, it's going to be negative 2V, right? So no matter what, I'm going to end up with a negative answer. Can inertia be negative? No. And the only way to get a positive J would be a negative times a negative, right? So hopefully that answers D for you. And then now see the pitch throws this parallel to the ground with this speed. Batter hits it. What is the ball's lost just after leaving the bat? The bat applied an impulse of this to the baseball. Oh, it's like putting it into that equation we just used to understand the one above. Cool. So now I just start this again. Let's see. They told me that J was negative 8.4. 0.4 Newton seconds. They told me, I'm going from here, by the way. They told me the inertia was 0.1145 kilograms. They told me, I'm gonna move that over. They told me the initial velocity was positive 32. So this is the one I don't know. Minus positive 32 meters per second. And they want to know V final. Anyone need help mathematically solving for V final? You're good? There's lots of algebraic ways you can do it. What I would personally do is get the 0.145 over on the other side. so that I had just V final minus 32. So someone did ask me to do it, so sure. I'm going to divide both sides by 0.145 kilograms. That'll leave me with V final minus 32 meters per second on this side. And then I'm just going to rearrange, bring that over to the other side. Since it's subtracted, I'm going to use addition on the other side. So plus 32 meters per second. That'll equal my V final. So then it's just putting it in the calculator after that. Any questions on that one before we move on to the, hopefully the next couple? Good. All right, so this will be a bullet fired. So we have bullet fired horizontally with this speed into a wooden block. Becomes completely embedded after the block comes to rest. Then the bullet is the block and the bullet is traveling at speed V final. Oh, okay. Oh, they kind of almost, well, they haven't really done our diagram for us because they did, this would be a velocity diagram. And what type of diagram do we need? A momentum diagram. So, but some good things to note, like, hey, what type of collision is this? Anybody? Inelastic. You could say perfectly. Do they use that term? Yeah, because they're trying to, differentiate between what I said. My vocab was semi-elastic. The book uses partially inelastic, perfectly inelastic. So I'd say perfectly, yeah. Every author has their own little things on here. So in an inelastic collision, momentum is conserved. That's easy, right? Because that's in every collision. Is kinetic energy conserved? No. Is velocity conserved? No. The only thing that's conserved is momentum. I'm going to make myself a note. 2 bodies before, 1 after. Just to remind myself. So down here in my diagram, I'm going to have my block and my bullet. And then in the middle here, I'll have block, and I'll put my bullet just a little bit inside. And afterwards, block with the bullet embedded. Here, I'm going to call that momentum final of the bullet and the block. Beforehand, I only had the momentum of the bullet. This was 0. And here, I would have a change in momentum that way and a change in momentum that way. This would be on the bullet, and this would be on the block. Maybe I should add a L for the block. And then I could put my forces in there, but they're not really needed. But that's what would get you, remember, that's 60% of your Y is doing that diagram down there. All right? Before, during, and after. Yeah, I would give you the sheet, the right sheet, to help you clue in on that, because I know it can be hard to pick. But anytime you see a change, you asked about before and after. We could have even done it on the baseball one. That one was really more about impulse. So, yeah. It could never harm you to do it. No, only really on the before and after questions. But, if you put them on everyone, you'd be fine also. Okay, and they want to know, let's see. Oh, we answered that. We answered A. We answered B. What is the speed of the block after the collision? in terms of VI, W, B. So they don't tell us. We need to pull our equation. Let's see. Our equation for momentum being conserved is that one. And it'd probably be good just to remind ourselves that we have that equation for momentum. Those would be the equations you should put at the top for, credit for writing valid physics equations. So let's see. So before the collision, the system had momentum of the bullet, but no momentum of the block. So I'm just going to put +0 there. Afterwards, you had the momentum of this new body, the block and the bullet together. So this would be the inertia of the bullet, the velocity of the bullet beforehand, equals, now I can't remember, did this class like me to do, well, it doesn't matter, everything's moving in the same direction, right? So everything's positive, right? Then here, for the inertia of the bullet and the block, you'd have the inertia of the bullet plus the inertia of the block, and now the velocity of the bullet and block together. And that's what we're looking for, right? That's what they asked us to find. Expressed in terms of VI, VW, and V. So, the wooden block, they say, is MW, so we'll change our notation. Bullet is MB, and the original speed of the bullet is VI. So, putting this in their terms, I've got MB, VI equals MB plus MW times VBW. So just rearranging over MB plus MW equals, and that's it. Nope, they didn't give us any numbers. They said solve it in terms of these variables. So you put those variables into your answer. I just did math. I just rearranged. That's math. No, that's why you have an equation sheet. Always, and every time. Did you have it on the test? Okay. They're still giving to you though. All right, so since it is a before and after one, we need to make sure that we have a before and after sheet so we can do our before and after diagrams. This was 7.96. So, what can we say about the momentum in the system? Always conserved. Good. If I had to classify this, what type of classification would I give it? Is it an inelastic, semi-elastic, elastic, or an explosion? It's an explosion. One body to start, two after. kind of how you classify and close. Please don't beat on the couch. They got to last a few years, like 30. That's one way you can kind of identify an explosion is that you have less bodies before than you have after. So momentum's conserved position, so that means to stay the same. Beforehand, we have no relative motion, so we're at 0, and then afterwards, we have some motion. So beforehand, there's my satellite, there's my astronaut, and they have no momentum, and then during is when the astronaut actually pushes off, and then afterwards, we have this. So here, none. Here, we have an impulse, let's say, on the satellite, and we have an impulse on the astronaut. Afterwards, we'll have a momentum of the astronaut and a momentum of the satellite. Oh, and then we should probably add in up here the astro will take time at a constant velocity to reach, is it the shuttle? Station, thank you. So, let's see. We're going to start off with this idea of momentum. So let's grab our momentum equation. Same two as we had last time because momentum is conserved. That one and that one. And I know eventually we're going to need it, so I'm going to grab that one in a very poor manner, but put that like here. All right, so I know the momentum before is 0. So what's the total momentum after? 0. So momentum of the system beforehand, 0. That equals the momentum after of the satellite plus the momentum after of the astronaut. And those are in opposite directions, right? So I could say, which way do you guys want to call positive? The way the astronaut moves or the way the satellite moves? Astronaut, okay. So we're calling that direction positive. So that would mean this one would be negative plus a positive here. Notice I've dropped my vector symbols because I've taken into account the direction with my positive and negative. You okay with that? All right. So also this, so I could rearrange it to say momentum of the satellite equals the momentum of the astronaut, right? So the inertia of the satellite, speed of the satellite equals the inertia of the astronaut, speed of the astronaut. Let's see, what information they give me. They give me each inertia and the speed of the satellite. Actually, the velocity of the satellite. So let's go back here and put those things in. 1,300 kilograms, 0.14 meters per second equals 92, was it? 92. 92 kilograms. VA. So VA prime equals, let's see. So I got, how many sig figs should I have here? middle of because it's not an answer, right? They didn't ask me to. They just want to know how far away they were. So I'm in the middle of the problem. So keep all my sig figs. It was a trick question on a Tuesday morning. Sorry. All right, now I'm going to use this because they move some distance. So I know how far they moved. I'm going to call where they started 0. So they started 0 meters. They moved at 1.9786 meters per second. And they moved for a time of 7.5 seconds. Oh, look, that number's already in there. I don't have to type it again. All I have to do is multiply by 7.5. And I get 14. Now, here's where I am giving an answer, so I should give it to like 3 sig figs. 14.8 meters. So that's how far away they were from the satellite. Any questions on that one before we try another one? Your numbers might be different than mine. I'll try mine to make sure. Okay, you have different time? But it's good for me to check mine because I've been known to make mistakes. But I did this time.